This is Bitophysics number 70. And you've got the link there on the first page to all the previous Bites of Physics and my growing list of public documents, treatises on various little topics that you can peruse if you like, complete with animation, or not animations, but drawings that I try to put together when I can't find one that suits my purposes. Today I kind of stole most everything off the web because it's pretty simple to do. So let's move right out into slide 2 with the question: does constantly moving west equal not turning? And you can see I have drawn there on a Mercator projection several pathways that could be traveling west from Spain to New York, from South Africa to Rio, from Santiago maybe, or somewhere in Chile, over to Sydney, Australia, from Los Angeles to Tokyo. Those aren't, I mean, I'm being a little loose with my latitudes there, but paths that go directly west. It certainly looks like those are not turning paths. You would constantly, of course, simply follow your compass if you had a compass that didn't suffer from magnetic deviation problems, which I don't want to get into. We'll, for the purposes today, we'll assume we somehow have a magic compass that really does know true north all the time, and so gives you true headings. These would all be paths that have a heading of 270 degrees. It's probably worth getting that out of the way right now. When we talk about compass headings, we always measure clockwise from north. So north is 0 degrees, east is 90, south is 180, and west is 270. So these would all be paths, headings of 270 degrees, or of course 90 degrees if you simply went the other way along these paths. So does constantly moving west equal not turning? And I haven't really said what turning is, I suppose, but what do you think? Anybody want to chime in?
Is it the same question as saying going west all the time will get you back to where you started? Is this the question?
Well, that's not the question, but I guess I would stipulate that moving west all the time will bring you back to where you started.
Right. So if you're walking in that direction, then relative to, let's say, if we define north, then you're moving. How should we do that? Okay, if you have a compass with you, then that compass would not change.
Right. That's really what I'm saying.
That's what heading west means, which means you're not turning.
Okay, that's so. There's one answer. Andy.
Yeah, I guess you have to talk about what it means to turn. But if you start moving, okay, if you're anywhere other than the equator and you were moving west, if you started moving west, and if you had a way of not turning, like making sure you didn't turn, after a time, if you look down your compass, you'd realize you're no longer going west. So you would have to turn to maintain a western direction. So yeah, you turn. I think the obvious way to do this is to place yourself near the North Pole and ask the same question.
Right. So if you do head west, start heading west, and you continue traveling straight, what do you find yourself doing after a while?
Well, wait, say it again. So if
I start in Los Angeles, say, and I start cruising west from Los Angeles.
Well, if you don't turn, you'll start heading south.
Start heading south.
Yeah,
that's right. And we'll get into that more. And as you say, maybe it's time to move to the third slide. Best way to really see that is to not look on a Mercator projection, but to actually look on the Earth itself. It becomes more and more obvious as you travel westward from a place that's close to the North Pole. Indeed, if you were 100 yards from the North Pole and you traveled constantly west, you would know for sure that you're turning, because you have to go around a circle that you would see your footsteps in the snow, I suppose, if there were snow at the North Pole when you happen to be there. Traveling around a circle of radius 100 yards. And in fact, you would always be turning to the right in that case. Right? And so maybe that's the other question. Does traveling west mean constantly turning right?
I'm confused here because we're kind of maybe I am confused. We're mixing the two geometries, the flat Euclidean and the elliptic, and the way we speak about those two things is quite different. So when you say turn in Euclidean and turn in elliptic, they mean two different things. So
Well,
so if you
don't
want to
have
really
to.
walk west, you'll be off the planet, no?
The
Like
best
if you
way to make sure that you're not turning really is to have a car, something that has two front wheels, and lock that steering wheel so that those front wheels are always in line with the back wheels. And if you do that, you will not turn. Now, this is of course in the in the limit of a perfect world where you can really get those tires exactly straight ahead, exactly in line with the rear wheels, where the surface you're traveling over is perfectly smooth, doesn't have bumps and all of those kinds of things. In other words, in a physicist's world where cows are spheres and all of that kind of thing. But I think you can, if you take that as the definition of turning, then clearly that car, when you're 100 yards from the North Pole and you want to constantly travel west, there's no question that you're turning. And if you think there is, then start 3 yards from the North Pole and try to travel constantly west. It certainly becomes clear at some point that you're always turning to the right.
all right, but the definition of continuing constantly west will guarantee that. No, because you have the compass in your hand. I'm really confused.
Well, no. So the point is, yeah. Go ahead, Andy. Maybe you.
Well,
You
I
take
think
this.
I think we need to establish what a straight line on a curved surface is, and then once you have that, you deviating left or right of that is turning.
That's what I'm saying.
Yeah. So a straight line. So how do I say this? A line of latitude is not a great circle. A great, like if you're to start in Los Angeles and head west, start west, and travel in a great circle, you will cross the equator on the other side of the Earth, and then come back to the northern hemisphere. No, you would
You'll cross the
and,
equator in the Pacific, probably.
yes,
in
yes,
that
yes,
case.
come
Yeah.
back to the equator on the other side of the Earth, and then go north. And so, anyways, to maintain a straight line, your heading is actually constantly changing.
Yeah, that's right. But I do think. I mean, I hope at least, Shamash, that you would concede to me that if you start a few yards from the North Pole and you constantly travel west, there's just no question that you're turning.
Oh, you're turning every time. I'm not debating that. I'm just asking whether you can call it turning or not.
Mm-hmm. Yeah. Okay, that's right.
Wait a
So
minute, because you could just make the argument the Earth is turning underneath you, and it's the Earth that has to do the turning, not you.
well, I don't think you really can because you are driving along in a car, and there's no question that the steering wheel is turned to the right. If you start close enough to the North Pole, you are traveling around a very obvious circle, and you know that to drive around a circle, you definitely have to turn.
Well,
So
you don't have to at the equator.
Okay, that's right. So you're anticipating, of course, the next question, and that's exactly right. So I asked, is it all if you accept? And Shamash, you're right. Of course, it is. The question is, what do we mean by turning? And that's why, and that is a good question, and I hope it does
Wait, we know
answer
what
it.
we mean by turning, because turning is the thing that sloshes water up on the side of a bucket. It's absolute.
Yeah, well, we don't have to actually talk about kind of inertial effects of turning, I think. All we really need, in fact, we're
What are you
really
talking about? Rotation is absolute, and we have a way of measuring it. So where are you
that's
going?
true. That's true too. But rotation and turning may actually be kind of different things in some sense. Anyway,
I
this
object.
whole bite of physics, I was a little hesitant about it because in some sense it really isn't physics at all. We are doing pure math here, pure geometry, and some semantics, as I think Shamash carefully points out as well. Is it turning if you keep your compass bearing heading west? You could just say, well, that's not turning. And I agree. You could semantically, you could decide to call that not turning. And that's why I just want to be clear that I want turning to mean driving in a vehicle that you can set on a straight path, a perfectly straight path, and that knows when it is turning to the right or the left. And that's a nice characteristic of vehicles like cars, is that they really can do that. They don't do it perfectly, but if they could do it perfectly, we would all understand that whether we are going straight or turning. Anyway, Benjamin, if you have further objections, feel free.
Oh, there'll be
Well, I
further
just
objections.
think that anything that sloshes a bucket is turning, and anything that doesn't slosh a bucket is not turning.
Yeah, I guess I would call that. I mean, when you say sloshes the bucket, it's a little bit vague as to
Doing
specifically
it
what you
at
mean.
constant speed, doesn't it solve the problem? Like if
Well,
you
let me say this another way that's more precise, that produces concavity on the surface of trapped water.
Right. So now we're talking about rotation and its dynamical effects, and I don't disagree with you, but I don't think it's important for this conversation.
Yeah, we can
Okay.
also talk. We don't need to talk about dynamics. We can talk about a geometric
Right.
notion of a straight line on a curved surface and define that without any need to talk about something moving along that line. Right.
Right. That's right.
Mhm.
That's right. It's useful to think about a thing moving to kind of define the straightness, but really the thing I'm talking about is pure geometry, not really physics at all. Okay, so if that's okay, at least for now, let's see. So what did I say there? So I showed you. Yeah. So we still haven't really answered the question. Does then moving west mean, but with my definition of turning, does moving to the west mean turning to the right?
In the northern hemisphere, yes.
In the northern hemisphere, right? And that's what, if you look at the diagram on page 3, you could maybe believe that it's true in the southern hemisphere too. But what is that the result of?
Projection.
Oh, come on, you know the word. It's you said projective, I think. Is that right?
I was going to say projection.
Projection. Yeah, I was going to say it's the result of perspective. That's the famous word that we use.
ah
I was gonna say that.
Yeah. Oh, Richard, you were coming up just to say that, weren't you? Sorry, I saw you too late. Okay, that's right. Because if you actually turned this globe a little bit so that you were looking at the South Pole, you would notice that that line I've drawn from South Africa over to South America is actually one which would require you to turn left as you are moving westward. And I think the same arguments, if you just imagine closing in on the South Pole and moving west, should serve to make you understand that as well. Tell a little story related to that. I once got into a conversation with a flat earther about this very concept. He was a guy who had served in the Navy, and he knew very well that to travel westward in the northern hemisphere meant to constantly turn to the right. He really did understand that. I was kind of blown away just by that fact, that a flat earther would have that kind of grasp of geometry to understand that. But it was particularly interesting because the classic flat earth model, the so-called Gleason map, would have you turning right when you travel west, no matter where you are on Earth, because the Earth, the Gleason model of the flat Earth is a circular disk in which westward always means traveling clockwise around the North Pole. And so we came to agree. He understood why I was saying that at the equator you wouldn't turn, and that in the southern hemisphere you'd have to turn left. But he disagreed with that and said, no, everywhere on Earth you have to turn right, because he believed in the Gleason model. And I agreed with him that his model had that entailment. I love that word, entailment, Shamash. Thank you so much. And we both agreed that the arbiter would be what actually happens in reality. If you do turn left in the southern hemisphere, then that would mean that the Earth is not described by the Gleason model, and if you didn't, it would mean that the Earth is not described by the globe model. And I thought that was an amazing meeting of the minds, one of the best meeting of the minds I've ever had with a flat earther. So, okay, so here we are, slide 3. And any more comment on that before we move on? Let's see, is there anything in the chat? Or what are we doing here?
Just mentioning that we are live on YouTube for the very first time. And I'm going to paste the link right now. I just had a little bit trouble setting the audio, but we are fine now and loud and clear.
All right, very good. Let's see, let's see, what is Sam asking up there? What's the difference? Between a Rhumb line and a latitude line. That's a good question. We'll get to that. We're going to be talking. You can already see that a latitude line is a Rhumb line. Actually, I haven't defined Rhumb line yet. I have to get to that, but we will. Yeah, it looks like a lot of good things. Oh, and something I have to see from Robert. Robert put a link I need to look at later. Okay. Rhumb is the minimum time course to the Rhumb. Yeah, that's why I started off with Little Feat's Rumba Man. I was thinking about whether I should go with Rumba or something to do with rum. Rum, I figured, would lead me to Jimmy Buffett, and I didn't want to do that, so I stuck with Rumba. All right, let's move on then to slide 4. Rhumb lines on a Mercator. In fact, did I? Oh, okay. Sorry. On slide 3, I guess I didn't emphasize enough. Rhumb lines are lines of constant compass heading, or bearing as it is. And so all the lines we've been talking about are lines of constant 270-degree bearing or 90-degree bearing if you travel in the other direction. And that is to say, in answer to Sam's question early on, lines of latitude are Rhumb lines, because to travel along them, you travel along a constant compass bearing, a constant true north compass bearing. So one of the great things on slide 4, one of the really great things about the Mercator projection, what makes it a genuinely valuable map for navigation purposes, is that it does tell you that it preserves directions and shapes. So the shape of Greenland is basically right. It can't preserve the shapes really of large objects, but it does as good a job it can. It preserves the shapes of smallish objects. And so it does a nice job of showing the shapes of things, but it gets their sizes completely wrong as you get further and further away from the equator. But it also preserves direction. So if you want to know what direction you have to travel from, say, Savannah, Georgia to get to London, England, I think that may be a fair representation of the line in the middle there. Then you just draw that line on a Mercator map. And if you just constantly move in that direction, you will get to London. The lines, a Rhumb line crosses every line of longitude with the same angle. And so that means your heading is always the same. In that case, it looks like it's about, what, 70 degrees or something, 70 degrees clockwise from north if you're traveling from Savannah to London, say, in that case. And then I show a line from Los Angeles to Sydney or vice versa. And it also has a constant direction, a constant bearing. In that case, probably more like 45 degrees or 225 degrees, something, depending on which direction you're going. Okay, any comments on that? So that's what a Rhumb line is, and one of the, and really the important thing here is that a Mercator projection allows you to determine the direction you would have to constantly move along in order to get from one point to another, with that way, to get there that way. Notice I'm not saying, although it looks like it on a Mercator projection, I'm not saying that's the shortest path, but that is the Rhumb line path. Any comments on that?
So all lines of latitude are Rhumb lines, but not all Rhumb lines are lines of latitude.
Exactly. And it's also, maybe this is a little early to be saying it, but it's also the case that all lines of longitude are Rhumb lines. Right? We to travel along a line of longitude, you move directly south always or directly north always. So that's nice to know that lines of
Except they
longitude
switch.
and latitude are Rhumb lines. Go ahead.
Except they switch from north to south
What do you mean?
at the poles.
Oh, yeah, that's right. Yeah, that's true. Yeah, that's right. Yeah, and that'll be a point that I return to at the very end today as well. So let's look at slide 5, where I compare a Rhumb line to a great circle, looking down on that path, maybe from Savannah to London or whatever that represents. I show a Rhumb line there as well as I could. I've kind of sketched a Rhumb line, and I've also sketched a great circle. Hopefully you can imagine that black line is maybe what you would get if you held a string tight at Savannah and London on a globe and then pulled it as tight as it could. It would kind of snap to the shortest distance. It would bulge out, right, because the Earth is a sphere. But there is that shortest distance, which turns out to be a portion of a great circle. That path lies on a plane that intersects the Earth at Savannah, at London, and at the center of the Earth. Take those 3 points, that defines a plane. That plane divides the Earth in two, and the place where it cuts the Earth is a great circle route that runs in particular from Savannah to London. I don't know why I keep saying, I don't know why I even chose Savannah to London. I wanted a path that looked like you could actually do it between places that people might actually travel between. Notice that the Rhumb line, if you tried to ask, well, what is the heading on that Rhumb line? Just look at the way it crosses lines of longitude, and I think you'll agree that it kind of crosses every line of longitude, maybe 70 degrees away from north. If you start at Savannah, the first longitude line there it crosses is clearly less than 90 degrees. I would say probably 70. And if I drew that correctly, all of those crossings would have the same angle. And I think you can kind of convince yourself that it does do something like that. In marked contrast to the Great Circle route, which, I'm going the wrong way. Of course, I even said on the thing I'm starting at London and going to Savannah. In the Great Circle route, you kind of start out a little bit above west. You start off moving, it looks to me like you maybe start out moving a little bit northward, but rapidly end up you start crossing the longitude lines at bigger and bigger angles until by the time you get down to Savannah, you're crossing those lines at a bearing that I would describe as maybe 230 degrees. That's 180 to south plus another 50, maybe, something like that. So you see that the Great Circle route, which is the shortest distance between the 2 points, requires you to constantly change your compass heading, your bearing. Any comments on that? So the Great Circle route is the shortest path, and it also is the path that, if you got rid of the water, just made a nice smooth surface, and you got in a car with perfect wheels, perfect steering mechanism, and you set those wheels for straight ahead, the Great Circle route would be the route you would follow. The shortest path, the straight line from London to Savannah, all of those things. And it involves constantly changing your bearing. And that's the maybe kind of interesting, somewhat hard thing to grasp at first, but not that hard. Probably most of you have it by now. Any comments on that before we move on?
So here's a question. How is the Earth round then? Because airplanes fly and they don't change direction. There you go.
Well, so when you say they don't change direction, now that's that. I mean, maybe I have to take. I would say they don't turn, but when you say they don't change direction, what do you mean by that?
Whatever the flat earthers mean. I don't know.
See, I think that's really an important point too. It is a semantic point, and that's why I would say that traveling a Great Circle route involves no turning, but definitely changing direction, in the sense that direction is indicated by compass heading. It's not easy. I mean, it's maybe the really important point is just to understand that it's not easy to follow a Great Circle route, because especially when you're in a plane or traveling long distances, it's really hard to know whether you're turning or not. It isn't a matter of just traveling straight, because it's really hard to just travel straight. If you want to travel on a Great Circle route, you have to have some help, something to tell you at every point if you're on the path or should be a little over to your right, or what direction you should be heading right now to stay on that path. Great Circle routes aren't easy to follow, because it isn't easy not to turn.
John, I was just trying to see which slide we were on.
I'm on slide 5, Rohan.
Okay, cool.
Okay, so and feel free, Rohan, if you want to kind of quickly catch up and ask questions, that's fine. Don't worry about if we've already talked about something. We can kind of quickly say it again. Okay, so let's move on to slide 6. Practical navigation. All this whole business of Rhumb Lines isn't very important these days, because we have lots better ways to do things. But back in the days when we were sailing the Atlantic, and that was kind of where most navigation was going on, there were a lot of other considerations. So before the era of accurate seagoing clocks, first of all, it was difficult to determine one's longitude. If you've never read the book Longitude by Dana Sobel, somebody help me. Dana Sobel, I think. Anyway, it's called Longitude. It's a wonderful book that explains the magnificent race to try to create an accurate clock that people could take to sea for months on end, because that was absolutely essential to knowing your longitude. You could see, the sun rise and the sun set, and if you knew what time it was, you could tell where you were east-west on the earth. Otherwise, you just say, oh, sunrise, it must be 6 a.m. or something. Right? Well, yeah, it's 6 a.m. locally, but the question is, what time is it back home, so that you can figure out how far around the earth you are? That was a really difficult problem. Latitude, on the other hand, is really easy. All you have to do is look at how high the sun gets in the sky. You know what the date is. You know how high it should get. You can look at Polaris at night. You can look at any star that you know the position of in the sky, and very quickly determine what your latitude is. So there were lots of good reasons to sail latitudinal Rhumb lines. One of which would be that if you, well, let's just take the example of going from, say, Lisbon to Cuba, the West Indies, which was kind of a classic thing to do. A good way to do that for two reasons would be to travel kind of quickly southward. You don't have to hasten yourself southward, but while you're traveling westward, travel southward until you get to the latitude of your destination, especially if you have reason to believe that there aren't any islands that you don't want to hit on the way. If there's no land masses on the way to your destination, then once you get to your latitude, you can just sail that Rhumb line, just staying at that latitude, which is easy to see. Just take sightings with your sextant, figure out what latitude you're at. Just stay on that line of latitude until you get to your destination. So that was a pretty way to do it. And it had the added advantage that the trade winds are such that they're usually behind you down there at lower latitudes like that. So they're pushing you, especially if you have a square rigger that doesn't do a very good job of tacking against the wind. Andy, you feel free to jump in if things occur to you here. You're a much better navigator than I am.
Sailing wise. By the way, I'm so excited that you're talking about a sailing related topic. This is great.
Yeah. Yeah, and this is both Andy and I have been avidly watching the Vendée Globe race, which has, if you don't know about it, it's going on. You can look up Vendée Globe. Wonderful website to kind of track the participants going around the world, single-handed, nonstop, no help, in 40-foot type, I think maybe 40 plus maybe foot boats. 60-foot boats, okay, that have hydrofoils, and that do 20, 25 knots in 15-knot winds. They've gone around the world, and I think the leader now is probably due in what, about 4 or 5 days, maybe? Do you think, Andy?
Yeah, it looks from a global perspective, it looks very close. But yeah, they still may have a few days.
One of the most interesting things to me is I think the leader is about 1,600. They're coming up the Atlantic to the finish line in France, and is about 1,800 miles, maybe 1,600 miles now away from the finish line. Whereas the last boat in the race is 8,000 miles behind. I just love that, a sailing race. This poor sap is going to be sailing for at least another month after the first person finishes. But it's really been fun watching that. And then and the winds are, of course, a consideration for them. They have different wind desires than the square rigger did. Square rigger loved to have a wind behind it, blowing it across the ocean, and that's what the westbound route on this largely kind of takes advantage of, is the fact that at lower latitudes the prevailing winds are westbound. So you get your Rhumb line, you get your wind, and so on. In between that westbound path and the eastbound path is what's called the horse latitudes, the center of this gyre that has wind blowing eastbound up at upper latitudes, and that you didn't like to get stuck in because you could kind of get stuck out there and not have much wind for a long time. But so eastbound, the idea would be to travel northward at a leisurely pace while you're traveling eastbound, and then get to the latitude of your destination and just follow a Rhumb line until you get there. Now, because of the way the winds worked, it's maybe worthwhile going a little further north than your destination. The worst thing you could do is run into Spain, maybe a little too high, and then have to come down. In other words, all sorts of considerations go into this. The winds, not running into things in the middle of the night. But it's just interesting to realize they had a whole set of different practical considerations, of course, back in those days than we did now. Welcome, Hermes. So, any comments on this or anything else, Rohan? You caught up with us?
Yeah, I'm good, John. I'm good.
Okay. So, all right. Well, then let's move on to slide 7. What about Rhumb Lines for air traffic? And so I chose this as an example here. San Francisco and Athens. They were the first two that occurred to me. They're both about the same latitude. So one could imagine just flying a plane with a constant. If you're going from San Francisco to Athens, just fly east, fly exactly east the whole trip, stay at 37 degrees latitude and get there. Now, you wouldn't do that for lots of reasons, one of which is just winds. Planes like to take advantage of the winds of the day. And nowadays, you know what the winds are blowing right now. So it's maybe worth going 100, 200, 300 miles out of your way to catch some favorable tailwinds. But the difference here is that the Rhumb line from San Francisco to Athens is about, I calculated, about 6,926 nautical miles, where the Great Circle route from San Francisco to Athens is a little more than 1,000 miles shorter, and that translates to 2+ hours of flying time. So you wouldn't do that for economic reasons, for passenger comfort reasons, and just for all sorts of reasons, including there's just no reason to do it. You're not trying to not run into things. There's no practical reason that would motivate you to fly a Rhumb line. So planes do fly pretty much that Great Circle with daily differences due to the winds, trying to get the most favorable winds and so on. And by the way, while I'm on it, the nice thing about a nautical mile is that every degree of latitude, when you travel north or south by 1 degree of latitude, that's 60 nautical miles. There's 1 nautical mile per angular minute of latitude, 60 of them per angular degree. So a nautical mile is a nice unit because there's 60 of them in every degree of latitude along a longitude line. And there's 60 of them for every degree of longitude along the equator, but only the equator. Right? The equator, like lines of longitude, is a great circle. Other lines of latitude are not. So the degree of latitude anywhere else will be less than 60 nautical miles. And then I don't know where I guess the translation from nautical miles to miles, I don't know what the history of that is. There was
nice one. We're still using metric, sorry.
yeah. Yeah, well, we have an advantage over you, Shamash. We use both.
Ooh, use gallons and pints and whatever that.
There was a great Saturday
how much
night.
have you lost? Oh, I lost 2 stones. Okay.
There was a great Saturday night skit on a replay, I think, just last week, or I can't remember the comedian's name. He was hosting.
Nate Bargatze.
Oh man, I've got to get the link to that where he's talking about. I think he's playing George Washington or something. Is that it? And he's talking about how it'll work in the new world and the decisions we'll make about units. That is one of my favorite Saturday night skits of all time. It makes fun of the English system in a brilliant way. Okay, any other comments on that?
Wait, so Robert in the comments says, that's a coincidence, which I think is funny. It's not a coincidence.
That's quite a coincidence.
I think it's not a coincidence. It's fine that way. But if anybody's curious, the difference between nautical and statute miles is it's 15% difference. So you can multiply a statute mile by 1.15 and get so it's a fairly easy. In fact, I mean, it's close enough that you can kind of interchangeably use, miles per hour and knots. But a knot is a little faster.
Yeah, I usually do the conversion by saying, yeah, a nautical mile is a little bigger than a mile. That's the way that I do the
Yep,
conversion.
yep, yep. We also use different feet. There's
Oh, is that true?
there's two different. Yeah, there's a U.S. surveyor foot, and
Oh,
then there's an
no.
international foot. And guess what foot the U.S. uses? The international foot. Just for added comedy. But
So
surveyors actually
what's the
use
difference there? That must be really minuscule.
Oh yeah, it's out at like 6 significant digits.
Yeah.
But yeah,
Well,
surveyors use a survey foot.
I did not know that. Okay, so on to the next slide, slide 8. We're almost done. So here's a few interesting factoids about, one thing I didn't mention, by the way, is if you start at the equator, for instance, and travel on a Rhumb line at a heading of 80 degrees, what do you suppose I don't know why I didn't make a slide of this. Before going on to slide 8, let's just ask this. Suppose you start at the equator and you travel a Rhumb line of 80 degrees. What does that path look like? You just keep traveling 80-degree heading. What does it look like?
Wait, starting from where?
Starting at the equator. It doesn't really matter. Start anywhere, but might as well be the equator.
Is it an ellipse?
It's not.
It's a circle as well?
Wouldn't it be a circle?
No, it's not a circle either.
Oh, wait a minute.
Remember that, so here's a hint. If you're traveling at a constant 80-degree heading, you're always going north. Always.
Would it kind of spiral?
It spirals. Yeah. That's right.
Hold up. You are keeping a constant 80 degrees on your compass.
Right.
You're saying you will never go back to where you started that way?
You can't, right? Because you're always headed north a little bit. Always.
What do you mean you're headed north? You just
80
said
degrees.
That your bearing is fixed.
So 80 degrees is a little north and a lot east.
10 degrees north of east.
I
see what you mean. Okay.
So yeah, you're always getting closer to the North Pole, right? And you're really heading east while always getting closer to the North Pole. And that's a spiral.
Getting ever so closer to the North Pole, but never being at the North Pole.
Yeah, I think the question is what happens right at the North Pole? Do you ever get to the North Pole?
I don't think you do because again, you're moving 80-10. So
that's right.
Wow, I haven't thought of that one before. Hey, hold on a second. Yeah. This is nice. I wonder
I really
should like an infinite path on the sphere.
That's right. It has a name, by the way. What is the name? It's a blah. If you look up Rhumb line, it'll say Rhumb line or some word that starts with L. Somebody help me out.
I'll get you. Hold on.
Yeah. Anyway, yeah, so that's what you get. You always get Rhumb lines are always spirals unless they're lines of latitude or longitude. So while Shamash is getting that word.
Loxodrome.
There it is, a loxodrome.
Loxodrome.
Yeah, that's the word. Okay, good. So now we know a new word. That's the word of the day. Let's move on to slide 8, chapter 8. So here's some interesting factoids. All lines of longitude are Rhumb lines, and they're also great circles, which are, quote, straight, meaning no turning, meaning shortest distance. So is the equator, but that's not really relevant to here. Lines of longitude and the equator are all Rhumb lines. So that's first factoid. 2, second factoid, lines of longitude radiate outward from the North Pole. And then 3, on a flat Earth, those lines could never again meet at a single point, right? They're radiating outward from the North Pole. They couldn't possibly meet at a single point. But those lines do meet. You can travel along any one of those lines, never turning, and a friend can travel along another one, never turning, and you'll both end up at South Pole Station at that building. You'll end up at that building that I show at the bottom there.
Is this like Area 51 or something?
Yeah, in the sense that you can't go there, because there are people who would say that's true. Yeah.
So now we know that you're with them and you're lying to us.
Excuse me, I had to mute there. You hit my funny cough. So anyway, now you know I have to always get a few digs at the flat earthers in here, but that really it turned. I kind of realized this the other day, and it's going to be of increasing importance going forward, as we'll see. Maybe if we go to slide 9. So as many of you, but probably not all of you know, we had recently, a few weeks ago, we had what was called the final experiment, where Pastor Will Duffy took a bunch of flat earthers and globe earthers, globetards as they're known lovingly, to Antarctica to see if the sun circled around overhead like the globetards were saying. And as the flat earthers have been denying, it's been kind of one of the central denials for ever since the beginning of the quote modern flat earth movement. I always hate talking about the modern flat earth movement, but that started about 10 years ago. And one of the chief tenets has been that there can be no 24-hour sun in Antarctica. That would make it like the North Pole, and it can't, because the map they used was the map on the left here on 9. It's an azimuthal equidistant projection of the Earth centered on the North Pole, which where the lines of longitude do radiate outward from the North Pole, just like they should. They're straight. Azimuthal equidistant projections have this really nice property that the point that they're centered on actually, for the point that they're centered on, the direction to every point on the planet is given by the map. The distance to every point on the planet is given by the map. So it's really a nice map for doing that. But the problem with centering on the North Pole is it turns Antarctica into a, quote, ice wall, which is kind of convenient for them. They like that because it then keeps the oceans of the Earth from falling off the sides or something, if there are sides. It's not clear whether there is a side or whether that's just all there is, period. And the problem is that the sun can't circle around you in Antarctica because, that would mean it isn't circling around somebody else in Antarctica, and it circles around everybody in Antarctica. So Antarctica really can't be that way if the sun circles around your head when you're in Antarctica. And of course, they found that the sun does circle around their head. And they also found that they don't keep you from going to Antarctica. That's another article of faith with the flat earthers, is that you can't go to Antarctica because, quote, they won't let you. Well, it's easy. You just, sign up with commercial outfit that'll take you there. And that's what they did. So they saw that. So that's a real problem. And immediately we have now flat earthers casting about a little bit for what the new replacement model is for the flat earth. And one of the chief candidates is basically an azimuthal equidistant. This is actually a slightly different form of an azimuthal map, but centered on the equator rather than on the North Pole, because the nice thing about centering a map like this on the equator is it treats the North Pole and the South Pole symmetrically. You get a North Pole, you get a South Pole. It turns Antarctica back into a continent. That's nice because they have good reason to think it must be a continent now. And all that's really nice, right? You can get your circling sun in the summer, in the north, in the winter, in the south, around Antarctica and everything like that. But the problem is that, and you notice the lines of longitude intersect at the North Pole and the South Pole, but they're not straight, right? They're curved lines, and the lines of longitude are straight lines. So you got this real problem now. Straight lines can only have one point of intersection, and that leads explicitly to this map if you believe that the North Pole is one of those points of intersection. But that map can't be. So now you have to have some other map, and there is no other map. There is no map that has 2 points of intersection that doesn't require the lines of longitude to curve. The only way you can get non-curved lines of longitude that intersect at 2 points is on a closed surface. Doesn't have to be a sphere, but does have to be a closed surface. It can't be flat. That's the point. And so this will be one of the problems kind of going forward. So, any comments on that one?
One tiny thing, John, to add to that is the lines of longitude after you pass the equator going south. That convergence means that the distance between those lines of longitude gets smaller and smaller and smaller. And on their map, they get bigger and bigger. So I was trying to demonstrate it to them. You could just pick two of them and look at the distance, like find two longitude lines that land on two different cities in South America or something, and you can look at the distances, go south, and those distances should get smaller. And but on the flat Earth map, it gets bigger. So that's another funny thing to me.
Yeah, no, that's of course exactly right. What was I thinking about in that relation? Yeah. I was gonna say, as you know, Rohan, one of the one of the maybe craziest things I've ever heard, and when it comes to flat Earth, that is a very high bar, is the idea. Some of our flat earthers promote the idea that there are more time zones in the southern hemisphere in order to keep us from knowing, keep us from realizing that there's more space down there. They put more time zones in. And I don't know exactly how that's supposed to work.
It's called
But
fudging. I'm curious, John, was there any video of their faces when the sun didn't set? Oh, I'd pay a lot of money to see that.
the funny thing, I followed it pretty closely. They were live streaming from Punta Arenas, Chile, before they got on the plane to go to Union Glacier. And they were already in Punta Arenas, Chile, seeing the sun circle around north of them and then come down and set in the southwest. And then they saw the glow of the sun just underneath the horizon, traveling to the left, while it was just under the horizon due south. So they knew that in Punta
Right.
Arenas, Chile, looking south at midnight, they were seeing the sun. And so they were primed. By the time they got to
Right.
Antarctica, they knew what they were going to see.
Jig was up.
Yeah. And I think really the only thing remaining for them was to get off, because a lot of them still had the idea that maybe it was a mirror image or some kind of a projection or something. And you get off the plane in Antarctica and you are in the most brilliant sunlight you have ever in your life seen, because you are surrounded with snow that's reflecting it back into your eyes as well. And there is no question that that is the sun that you're looking at.
That's right.
Yeah. So it was pretty funny, but it was interesting. I mean, especially one of them, Jaron, who has now said that he is no longer a flat earther, because of the crap that he's been getting from the flat Earth community. I mean, he just said, right, wow, okay, this is clearly, I'm wrong. So good for him, even though he still knows that NASA lies. But that's another thing. We'll get there. Okay, let's move on to the last slide. Just a very a kind of a peripherally related question. These are a couple of maps. This is off of a website that Andy turned me on to, I believe, satellitemap.space, which is kind of a great thing to go to. The link there at the top. These are, on the left is just a picture showing the location of every Starlink satellite at the time that I took that screenshot. And on the right is the same thing, but after I clicked on one of the Starlink satellites, and it shows the paths, the recent paths of all of the satellites that were launched in the same group as the one that I clicked on, which is kind of interesting. You'll see that they launch satellites into a particular orbit, and then they kind of tweak those orbits to get the satellites like that. So this is kind of the final orbits for a bunch of satellites that they launched in one group from Vandenberg Space Force Base. Well, could be that, or Cape Canaveral. They're launching a group of these from Vandenberg, a little north of my place in Oxnard, almost once a week now. And you can see how many satellites there are. It's kind of interesting because if you look at this map closely, you'll see places where they're splashing them down. They come down from time to time, and evidently, I don't know exactly why. It's a malfunction maybe, and they bring it down and put something else up. But it's just interesting to look at this distribution of satellites. You can also see the orbits there. They're all orbiting, of course, on great circles. Orbits are themselves great circles, while the Earth rotates underneath that orbit, which is what gives that kind of weird ground track that you see when you look at it. But you'll notice the orbits themselves, of course, are perfect circles centered on the center of the Earth. Not perfect circles, I shouldn't say that, but almost perfect circles. And so on. So what do we learn from this? Why do they look? Why do the maps look the way they do? In particular, look at the distribution of satellites over the North Pole. Look at the kind of hard edge up there at some latitude. And of course, then look at the orbits and so on. What can we glean from this? There's a couple of fun facts kind of hiding in here. Go ahead, Andy.
Yeah, that's interesting. I mean, it could be because that's exactly where they want them to be, because they don't need to cover. Well, you don't have to go exactly over the North Pole to cover the North Pole, but you also don't really need to cover the North Pole so much. There's less people up there and South Pole, so it could just be that's like the most optimal place to allocate their assets. But also the geography of these launch sites are key. So like Vandenberg has access to pretty damn near south. I think that's why they. So if you want to launch a polar satellite, you launch it out of California. But everything out of like Florida's got to go east. So I think they're constrained by their launch site as far as which direction they can actually launch these things. So I don't know. I guess I'd bet more that they're able to put them where they want to put them, and that's why they're there. But it could also just be like a constraint.
Yeah, it's interesting to me. For a while, I was saying, I think wrongly, that only now are they starting to populate the polar region. I don't think that's right. As you say, apparently the main reason they need so many satellites is just bandwidth. They don't need anywhere near this many satellites if they just want to have coverage, if they just want everybody to be able to have access to one for cell coverage. But in the mid latitude regions, not so much mid latitude really, but upper latitude regions, you need a lot of them. And so there's kind of constrained by the fact that they have to, if you're going to cover America, you're going to necessarily cover everything down to, or the United States, I should say. If you're going to cover the United States and Europe, you're going to necessarily cover everything just as well, all the way down to minus 40, minus 50 degrees latitude, because that's just the nature of orbits. But there is that weird hard edge there at plus 50 or something, an Arctic Circle kind of a thing. It's not as far north as the Arctic Circle. I don't really understand exactly why that hard edge is there. It seems to me like it would kind of soften into the poles if they had their druthers. So there's some reason for that I don't understand. And if you do or somebody else, I'd be interested.
It reminds me of a ball of twine that you buy, like that they're not like a perfect ball. They wind them so that they're kind of like a toroid, and that it defines an edge on the top and the bottom.
Right.
It looks cool.
Yeah, and so we're joined by Jihuatzi. I knew I'd bring him up when I started talking about America. Have you got some nasty comment, Jihuatzi? Hihuatzi, sorry.
I never have any nasty comments. I'm a peaceful being. I'm a peaceful and rational being.
No, that's right. You are.
No, I was just going to ask. I mean, I already know the answer, but for people in the audience, if you wanted to explain why satellites appear, at least on a flat map, to have an oscillation.
Right. Yeah, and so I was kind of getting at that by talking about the Earth rotating under. If you look at those orbits on the right side, and as you say, right, I understand that you get this, but to kind of put that out, if you imagine the Earth rotating eastward that underneath an orbit like that, you can see that if it comes around and comes down over San Francisco, this orbit, it's going to come down significantly west of San Francisco on the next orbit, and so on. And so that downward part of the orbit is constantly moving eastward about 1.5 hours worth of turn every orbit. And then, of course, and it's doing similarly on the south. If you imagine that it clearly oscillates between whatever the highest latitude that orbit gets to and the lowest latitude that orbit gets to, which is just the negative. If it comes up to plus 40, it's going to go down to negative 40 on the other side of the Earth. So if you unfold that Earth, turn it into a Mercator projection or something like that, you'll end up with a sinusoidal kind of a path which moves westward by 1.5 hours. What is that? 50, how many degrees is that? 1.5 hours sounds like, oh, I don't know. I can't work it out. 15, 22.5 degrees, I think, something like that. 22.5 degrees, I think, every orbit, something like that.
Well, online it says Starlink satellites have fewer around the poles because of the way their orbits are designed, with most satellites concentrated at mid-latitudes, resulting in less coverage near the poles due to the inclination of their orbits, which is optimized for providing maximum coverage over populated areas rather than sparsely populated polar regions. Additionally, the Earth's magnetic field can also play a role in the distribution of satellites around the poles, potentially causing some technical changes or challenges at high latitudes.
Oh, I don't know what that's referring to. Maybe
To
somebody
add to the
else
mix
might.
here, John, it may
Uh-huh.
be the Russians after all.
Yeah.
That restrictions over their airspace may be part of the reason why you see a hard line there. So that may be a third reason.
Yeah, it could be. I guess I'm skeptical of that. It certainly is the case. I mean, once again, to say the main reason, you don't need anywhere near as many satellites as we have to provide spatial coverage. As I understand it, it's just a matter of bandwidth. Each satellite can only handle so many calls. So if you want to be able to handle the number of calls that I guess they think they're going to eventually have, I don't know I can't imagine really that they have it now. You're going to need a lot of satellites. And frankly, I don't really understand why there are so many satellites now, because I don't think you would need that many now.
They're also quite low, so they're close to
Right.
you, which is less latency and faster communications.
Right. That's true.
Yeah, but then they travel faster because of that. So you kind of need more,
Yeah,
even when
so
they're on
yeah,
the same orbit.
they're in
Visible
view
for a
for
lot
less
less
time.
time.
Yeah, yeah.
Yeah. Yeah. That's right.
I was
You
just
only
going
get
to
them.
say that I was intrigued by the same question, so I asked my pet AI, and I don't claim to follow all of this, but it's due to mechanics, orbital mechanics, and satellite inclination. So specifically, I'll just read this paragraph. Most satellites in polar orbits have inclinations slightly less than 90 degrees, leaving a small gap at the poles where they do not pass. This occurs because sun-synchronous orbits, common for Earth observation, are optimized for consistent lighting conditions, creating a coverage hole at extreme latitudes. Additionally, satellite congestion near the poles increases collision risks, further limiting coverage.
Yeah, there is this interesting orbital thing that a particular inclination, or rather high inclination, causes the orbit to precess once per year. So the orbit always maintains the same orientation with respect to the direction of the sun while the Earth goes around the sun. I think that's what the sun synchronous orbit thing is referring to. And there are a lot of satellites in orbits like that.
Hey, John, but there's no reason why you couldn't have a satellite that like hits the North and South Pole,
No, I don't.
right?
Right, I don't think so.
I mean, if you can launch it. Okay.
But there's this whole thing
Yeah,
about the magnetic field. I'm not sure what. I think what Hiwazi said when in his, the thing he read. I don't know what that's talking about. The potential
maybe the
malfunctions.
Japanese wooden one wouldn't suffer from it.
The which?
They, the Japanese launched a wooden satellite like a couple of months ago.
Oh, a wooden satellite.
Yeah,
Really?
you didn't hear
No,
about it?
I didn't. No.
No, it was made of completely carbon-based material, like cardboard and wood, etc.
Is it a
And
bonsai tree?
They
but
origami it.
yeah, the origami. But maybe that one won't suffer because while passing above the poles. I don't know.
Huh. Yeah. No, I don't know. That's interesting. Let's see. So what was I going to say? Once again, okay, it's slipped my mind for now. Anybody else have a comment or a question?
Well,
I do
here
have a quick comment. Sorry, go
Go
ahead.
ahead.
sorry, it just says the magnetic field reaches its peak at the poles. Satellites can experience issues like electronic malfunctions, data disruption, and increased exposure to radiation due to the
Oh,
strong. Yeah.
I'm glad you said
that's
that, you know, because I was
that's what it
wondering
is. Yeah.
exactly what the impact was. Yeah, that's right. It's the solar radiation. Yeah.
Yeah,
As
up
opposed to just
there.
the magnetic, because it seems to be a bit weak to really do anything, you know, per se. But yeah, the way it channels the solar wind, for sure, I could see that being an
I
issue
should
because that
have I
definitely
should have
affects
known.
satellites. Yeah.
Right, I should have known. I did my PhD thesis on the aurora borealis. You'd think that would have occurred to me. If you're traveling through the auroral zone, then you have almost direct access to the magnetospheric and solar wind particles, high energy particles, and so on. So that's right, a lot more potential for disruption that way. I'm sure that's what they're talking. It's not really so much at the North Pole, but a little bit kind of sunward of the North Pole. Yeah, so that's interesting. Let's see, what was the other thing? There was something else I was thinking about. Oh, I know what I was going to say related to inclination. One of the really interesting things is that the International Space Station, so when you launch, one of the nice things about Cape Canaveral is that it's very close to the equator. Not really sat close to the equator, but it's almost as far out as the equator. So when you launch eastward from Cape Canaveral, you get a really significant boost. You're already traveling nearly 1,000 miles per hour in the direction you want to be traveling, 17,000 miles per hour. A lot easier to get there because you only have to boost yourself by 16,000 miles per hour. If you wanted to go the other way, you'd have to launch, if you launched a satellite westward, you'd have to give it an additional 2,000 miles per hour, one to count to get rid of the Earth's rotation and one to kind of gain it back again in the other direction. And so Cape Canaveral is a great place to launch rockets. In particular, but you can't launch them anything lower inclination than the latitude of Cape Canaveral. If you launch directly east from Cape Canaveral, you end up with a satellite that has an inclination equal to the latitude of Cape Canaveral. It comes up to that latitude and then crosses the equator because it travels straight. You launch it eastward, it travels straight and therefore crosses the equator. And then on the other side of the Earth is at the same latitude south of the equator and then comes back around again. And so you might think that in building the International Space Station, you'd build it in an orbit that has the inclination of Cape Canaveral. It'd be the most cost-effective, efficient way to get stuff up to the space station. But the Russians were going to be involved as well, and they launch from a a launch site that's significantly further north. So they had to put the International Space Station in a higher inclination orbit, which makes it less efficient to launch to from Cape Canaveral. And they had to launch it, and they had to put it into an even higher inclination orbit than that, because if you launch directly eastward from the Russian aerodrome, space drone, whatever it's called, you overfly China. And you really don't want to be overflying a kind of a, touchy-feely neighbor with rockets that might blow up on launch. So they have to launch a little bit to the north from their base to go into orbit, and that's why the International Space Station is in the orbit that it's in. It just goes up high enough to skirt over the northern part of China when that happens.
So the ISS never flies over China?
No, it does fly over China, but to reach it, you don't have to launch things.
I see.
The boost phase is never over China. Yeah.
That's nice. You know what else is nice? I'm reading about...
Oh,
you are.
No. Damn.
Wow.
Okay.
You're a tiny bit nice. I'm reading about those loxodromes. And if any nerds are around, the path...
Are there any nerds in the house? Raise your hand.
No. So apparently, if you fix your bearing and you go around the globe, you will spiral to one of the two globes. That's for certain. But the path is infinite.
Yeah.
All right. Your journey, sorry, I should be very careful.
It's
journey
a Zeno's
is
paradox kind of a thing, right?
But the length of the path is finite, and you can calculate the length of that path. And that is absolutely mind-boggling.
Well, so you say infinite. I think maybe if the length is finite, then if you travel it at a constant speed, it can't be infinite time, right?
The length of the path is limited by a certain number. But because you're constantly turning, you will never be able to do it in a finite amount of time. Unless,
so how does that?
You know what I mean?
But if the length is finite, then any velocity will get there eventually. Will get to the end.
You're wasting time turning. You will never get to your destination. That's the thing.
You have to slow down for turns. Obviously.
That's true. You got those signs, right? 10 miles per hour. No, but I think I object. It strikes me that I could imagine the length of the path being infinite. But if the length of the path isn't infinite, then all you need to do is travel it at any speed and you're going to get to the end.
This is the mind-boggling part. Will you ever get to the poles? We started that you will never going to get to the pole.
I do kind of believe that.
All right. So if you're never getting to your destination, then your journey takes infinite amount of time. That's it. You're constantly journeying.
But that also requires that the path length be infinite.
Not necessarily. No. It's one of those series when you're adding 1 plus 1/2 plus 1/4 plus 1, etc., and you keep adding forever. But that's a
Zeno's paradox, right?
It's not a paradox. Oh, okay. Now you're gonna make me make a room about this. Oh,
yeah, boy. I think all so. Right. Because I really do. I mean, if the length of the path is finite, then you can travel that path in finite time. I mean,
not necessarily.
It simply can't be the case. That can't be the case.
No. They're completely two different things.
I don't think so.
All right. Then note to self: we're gonna have a room about this.
Yeah, we're definitely gonna have this one out somewhere else. But we're still going to be friends. That's the great thing about science arguments, right?
Oh, we're going to be lovers. We're not. We're more than friends. We're lovers. The new year, we're supposed to... Come on. You promised me.
Not that there's anything wrong with that.
You promised me.
Okay, well, that's good. Oh, my God, this is all on YouTube, too, right?
Yeah, I put my love in the chat
yeah, we can.
Ago, 20 minutes ago.
Well, that's really. I mean, so I'll be interested in seeing. It looks like you're reading something that says all that. Is that right, Shamash?
Oh yeah. It's the Wikipedia page. It just said it right there, and they give you actually the formula of the. So they say the length of the meridian divided by the cosine of the bearing away from the true north. That is the length. So it's a
And
very easy demonstration.
and they say that it can't be traveled in finite time.
So okay, let me read again. They are close. All loxodromes spiral from one pole to the other. Near the poles, they are close to being logarithmic spirals, which they are exactly on a whatever, not important for our discussion. So they wind around each pole an infinite number of times,
Yeah,
but reach the pole in a finite distance.
yeah. But they don't. So they don't say that it takes. So they don't claim that you can't get to the end.
But if you wind around each pole an infinite number of times,
Yeah, that's not a problem, right? You can still
Wait,
do that
are
in
we
finite
traveling
time.
at a an angular velocity or a normal velocity?
Yeah, I was just thinking a normal
yeah,
velocity. If the length of the
yeah.
path, if you can tell me what the length of the path is, then all I have to do is, cover a tenth of that path in every unit time, and I'll get there.
But you will never get there. That's the thing.
And I don't believe that. It doesn't say that. I'll just point out that it doesn't say that, and I
It
don't think
says
that's
you're gonna
true.
go around the pole an infinite number of times.
Right. I get
Well,
that.
all
I
right.
get that. Yeah. But you can do that. You can in Zeno's paradox, you do an infinite. There's an infinite number of steps that you take, and you do it in a perfectly finite time.
Zeno's paradox, which one? The one that you
Oh,
are walking towards the wall, or the one that you are counting before you walk?
the one where you walk half the distance and then
Yeah.
half the
So
distance and then half the distance,
yeah,
etc. Right? You
yeah.
do
So
that an
you
infinite number of times, and you
in
do
a
it in a
finite,
perfectly
yeah,
finite amount of time.
yeah. But you will never reach your destination. That's okay. I see your problem now. Okay.
Zeno hadn't taken calculus.
Yeah. Yeah, no, that's right. It's different. It's different if you do each step in the same amount of time. That means you're slowing down, right? Yeah. So okay, well that's interesting. Anyway, I did want to look more into the properties of that. It is an interest. Spirals in general, of course, are interesting. That whole business of making an infinite number of turns and never somehow getting to the end, but still having a finite length. Just that by itself is a pretty weird idea.
Of course, the whole thing is a mathematical game. In the real world, you will get
Yeah,
to a point where you're stepping
you're
over 30 centimeters square of land and you don't know where to go. But yeah,
your damn shoe is already on the North Pole, but you're just getting closer and closer. You're getting the center of your shoe closer and closer to it, or whatever. Yeah.
yeah. Mentioning Zeno's paradox, Diogenes the Cynic, he walked on Zeno when he was, telling people that you can never start a journey because of the infinite thingy, and he just said, "Watch me," and he started walking. Like,
Yeah.
that's exactly what we're doing.
That's like I think I don't know if I've said it here or not. One of my favorite paradoxes, whatever, is I think it's called the hangman's paradox or something. The prisoner's told he'll be
Yeah.
hanged one day. Did we talk about that once? I think we talked about it. Says he'll be hanged one day next week, and he'll be surprised. He won't know what day, and he'll be surprised when it happens. And so he decides, well, it can't be Friday, because if it's Friday, I'll know it's going to be Friday. I won't be surprised. So that's out. So it can't be Thursday, right? Because that's the last possible day. Can't be Thursday. He rules out all the days and decides that he can't be hanged. And then the hangman comes on Wednesday, hangs him, and he's surprised. I just love saying that, especially the he's.
It sounds like a joke more than a paradox.
It does. It kind of does, but there's something going on there. All right. Well, this is good. This was fun. This is probably more like what a bite ought to be, a little more accessible maybe than usual, a little easier for me to put together. I'm going to try to move myself that direction. But as I say, next time, or at least sometime here, I want to talk about stellar aberration and Aries failure, because I think it's really an interesting topic. That might be a couple coming up. Look up Aries failure if you want to do your homework in advance. Any other things?
I'd just like to thank you, John, for doing this room, and that it's recorded, so I can send some flat earthers over to the recording to let them do a deep dive if they're honest in their intent to really know the truth. And one thing I've done to sort of summarize everything you said here today to the flat earthers is I tell them that I will be the first convert to flat Earth the day Flat Earth Airlines opens up and is actually able to make money in that
Yeah.
business. Yeah, because I mean, if the mere fact that no organization that has to navigate the globe, right, or the Earth, shall we say, as a point of business, is subscribing to any flat Earth model is more than enough evidence, I think,
Yeah.
in practical effect, to prove that the Earth is indeed a globe and not flat. So
Well,
that's
it's funny, I mean, along those lines, I just always point out we never proved that the Earth is a globe for thousands of years. All there was just fantastically compelling evidence that the Earth was a globe. It was a conclusion. We never proved it. And then about 60 or 70 years ago, we sent cameras into space, and it stopped becoming just a fantastically well-supported conclusion and ventured into the realm of directly observed fact. So I'm not worried about the flat or about them proving a flat Earth, because you can't prove that something is other than what it is directly observed to be. And in the case of the globe, so that and for me that really comes down to understanding the nature of the fact of what I say is that in science we never prove things. We prove things in our models, and then we see if those things that we prove in our models are observed in nature. But we never prove that our model is nature, and we never prove anything other than the fact that we have things better than proofs, and the things that are better than proofs are directly observed facts. Excuse me.
You
So
know,
yeah, go ahead. Go
I
ahead,
was going to
Simon.
say that there may be
Andrew.
no flat Earth Airlines that's going to survive for very long, but in Carson City, Nevada, there is a pizza joint called Flat Earth Pizza. Apparently, I've heard about this, and I hear they have pretty good pizza.
Well, you would expect, right? I mean, if anybody could make pizza better than a glober, it would be a flat earther.
Wow,
Life
what an
mission.
idea.
Yeah. Solon, you were going to say something. Welcome to the stage. I don't know that we've met.
No, we haven't. So I was going to say that their counter argument would be that nobody went to the moon, nobody went out in space and taken photographs. So whatever you throw at them, they will say that it's all fake.
Yeah.
Oh,
No,
believe
that's
me, we know that firsthand.
yeah. We do know that, but I just always think it's kind of interesting that we buy into that when we talk with flat earthers. We just kind of know right off the bat that we're not allowed even to talk about the fact that, that the globe is a directly observed fact. We have to fight the battle with one hand tied behind our back, but it's not a very hard battle to win anyway. I mean, I always point to the fact that no flat Earth model, it is literally impossible for any flat Earth model ever to predict sunrise and sunset times. That will never happen, and that should tell you all you need to know as well. In fact, it's impossible for the sun to set at all, except in that one model where the sun goes around behind it, in which case it's night everywhere, and it happens at the same time everywhere.
That's exactly the point that I made. And then I was making a suggestion to the flat earthers weren't there. So I was making a suggestion. If you take, for example, England, and if you take example, Tasmania, they're roughly the same distance away from the equator. All you have to do to tell the flat earther, find somebody in Tasmania and find somebody in England and record the sunset and sunrise. So that was my suggestion. But then somebody suggested what they are doing is that the sun is like the there's a tube around it, sort of thing, like
Yeah.
like a torchlight, and it moves around the globe. That's how you get different sunrise and sunset around the world. So you can't
Yeah.
win.
No, you can't win. That's really true. And it comes down to just, it comes down to those people. It's interesting with Jaron Campanella, one of the flat earthers that went to Antarctica, because he's come back and has pronounced himself not a flat earther anymore, although he's clearly not a globe earther, just because of the fact that he has been savaged by the flat earth community. They've thrown everything, all of the video that they took down in Antarctica. He's being subjected to exactly the dishonest attacks that he himself trained his audience to level against the moon landings. The lighting's wrong. The shadows don't work right. This flag is waving in the breeze. There's green screens being used. You can see the green screen here, whatever. All of exactly the same attacks that he trained them to level against the moon landings. And I don't know that will occur to him or not, but it's delicious irony.
May I add classic cult behavior too.
It is classic cult behavior. Yeah, that's true. Well, anyway, I indulge myself too much. It is such a funny love-hate relationship because I just have to acknowledge the fact that my interactions with flat earthers have really rekindled my love for going out and doing experiments myself, for thinking about things that I hadn't thought about deeply enough, and coming to new appreciations for arguments that I'd never really seen before. So it is, there is a major silver lining to it all. And I always have to try to convince my wife of that because she really doesn't understand it. I think I'm going to move towards shutting it down. I always say that, and then it stimulates a few more things, and that's fine if it does. But I'd like to finish up in 10 or 15 minutes, if not 1 minute. If nobody has anything more, we'll shut it down now.
Well, I'm anticipating a good sailing-related song from you.
Oh, wouldn't that be something? I know. Oh my God, can I do this? Let's see if I can do this.
How about Feeling Gravity Pull by REM?
Well, that's a possibility. I've got something in mind here. Let me see if I can find it. Here we go. Let's see. That's not right.
Well, till you find it, let me very quickly re-advertise my philosophy series. So every Wednesday, same time as this room, 17:30 GMT. I'm running a philosophy of science - math - logic series, where we talk about more theoretical problems than they are applied. And the last couple of weeks, we've been focusing on the theory of knowledge, scientific thinking, how does that build, etc. So we might be talking about scientific assumptions next week, or the theory of meaning. I still haven't made my mind. But every Wednesday, 17:30, if you're interested in the philosophy of science, you're more than welcome.
What room is that, Logic?
So it's called Philosophy Wednesdays. Every Wednesday at 17:30. Let me paste the link as well in the chat.
Thank you.
Okay, well, I think I found it. So I'm gonna play us out with an old live recording, I think, of my band before we got a drummer. This is the Jaybirds doing "Sailing," our yacht rock anthem. See you all, guys. See you guys.
How could you be a band without a drummer?
Yeah, well, we aren't anymore, but we were for a long time. We kind of started as an acoustic two-piece and then became a acoustic two-piece with an electric bass. Then we added drums, and then all hell broke loose, and now we're just a cover band. So, But we are kind of moving into yacht rock, and this is still kind of one of our anthems, even though this is a very early version of it. Thanks for coming, everybody. See you next week.